Okay, I think we can start our course. But before we start, let me make a polling. So let me stop the screen share. Let me make a polling. Just to make sure that we are on the same page. Okay. Oh, I think we just have 4 students. But yeah. Oh, fine, 5 students. But can you feel the poll? So we'd like to know the schedule for final. If you would like to have other schedule besides 6 and 9, I believe we can have also, as long as everyone also agree. Okay. Okay, so far, Thursday. The link will be open for only a few hours for the final. So we will have the WebEx meetings, and we have uh, the link. So we will have open cam for WebEx. You click the link. I will prepare at least two platform, using the same platform as your last quiz, and then also another platform for some short questions. Okay. Okay, I think so far, well, because this is just only 5 students that is in the polling. Uh, the schedule will be on Thursday, 9 of June. Okay. If you have any problem with the schedule, just let me know. But maybe at the end of the class, I will open one more time, see if there's other students that are coming at the end of the class. Okay, let me close the poll. Okay. Regarding the link, like you did the quiz, do you have any problem besides some trouble when you type in the link? You type in the answer. Is there any other problems? using the platform? I think everyone doing fine, right? I think the problem is just when you type in and it seems it doesn't going through the system, and when it's happened, it means that your browser, I think either you need to clean your cleaning. Let me write in the chat box, cleaning files. Clean your history, your case in the browser, or you could just use the private browser, or in the Chrome you can use incognito mode. Okay, I think that will be better options, okay, if you want to directly click the link. Okay, so you can use the incognito mode. Okay, back to the lecture. I think we can go to our lecture. I will start with the okay. I've attached in the last module. I've attached all the selected problems. Okay, this is the selected problems from the chapter 8. But I forgot to add the it's until 84. It should be I should have more about 92, 93 regarding the enthalpy chart, but make sure you read about that. Okay, make sure you read about that. At least one or two questions will be relatively have a correlation with the enthalpy chart system. Okay? Enthalpy concentration chart. Okay, it's the ammonia, the sulfate. Okay, the sulfate concentration and enthalpy system. Okay, and also I have practicing at least one or two questions. I have uploaded in the video I have uploaded, and I will attach the link later on today's Moodle. Okay, I've given you some additional examples and some additional what you need to emphasize on the chapter 8. So chapter 8, basically we are having the constructing the path, right? The path for our reactions. Okay, so we are having different types of enthalpy, right? So when we have the phase change, when we have raising the temperature using the CP, using the Clausius-Clapeyron, and so on and so forth, right? So that's chapter 8. Now chapter 9, we will have a different problem. So chapter 9, we will learn about the reactive. Okay, so every reactions, they will have some process, right? If we look on to the molecular, let me just go through a new page. Okay, so this is some example that I show you in the video. You can watch later. Okay. Wait. I'll take this. Okay. Okay. So chapter 9. So today I will talk to you about chapter 9. Balance on reactive process. So what is reactive? What is reactive? So if we have water, okay, so if we have water, it's the formulation of water came from the hydrogen and oxygen, right? So let me go through hydrogen and oxygen, and goes through by H2O, and let's compute the stoichiometric reaction. It's supposed to be gas. Gas. Okay. If we look on the molecular level, the constructions of this water is it came from the three chemical bonds, which is the two hydrogen, one oxygen. So we are having, we broke this bonding, right? And we construct a new form, right? A new form, and we construct 1, 2, 3, 4 bonding. Okay. So when it happens, of course, we are going to have some energy. Okay. Well, let me write energy release. Okay. Energy release, especially when water molecules bond form. Okay. And it's going to have more energy. Let me write energy release is more energy release when water molecules bonds form rather than break. It means that because it has a 4, this is 3, the energy in this 4 is higher. Okay, it's higher. So if we want to make the reactor as in a constant temperature, then the energy need to transfer away from that reactor, right? So if we take this in a reactor, this is the reactor. Okay. If temperature remains constant, then energy or heat, okay, maybe heat, or maybe net energy must be transferred away from the reactor. Okay. If not, then the temperature will be rising. It will be increased. Okay. So from here, we are going to break down our knowledge in the energy that is released or absorbs. Okay. So if the first process, the breakdown process, the first process absorbs less energy than, let me write in the first and then second process. Absorb less energy than second process releases. We call this reactions exothermic. Or maybe let me write in the new page so that I can write both exotherm and endotherm together. Let me copy this. Let me write in the new page. Okay. So we call exothermic, the product molecules at a given temperature and pressure have lower internal energy and also enhance the enthalpy. Then the reactant molecules. So the net energy then must be transferred from reactor as heat or work, or else the temperature of system will increase. This net energy we call the heat of reactions, and this will be one of our observation in chapter 9, the heat of reaction. We call the heat of reactions. So must be transferred from reactor as heat or work, or else its temperature will increase. Okay. If less energy is released when product create a forms or bondings, then it took to break, which means the form bondings is less than the breaking one. Okay, so the breaking bond, maybe when they broke the bonds is having more bondings than the forming one. Okay, so if the energy is less, okay, then it took to break the reactant, then we called its reaction is endotherm. Endothermic. Okay. So as a consequence for this endothermic, the energy need to be transferred inside, okay, not goes outside. So energy more clear. So energy must be added to the reactor as heat or work to keep temperature decreasing. Sorry, not decreasing, from decreasing. So we need to add more energy. If not, the temperature in the reactor will be going to be decreased. Okay. And of course, when we are talking about this exotherm and endotherm, we are talking about a large gap of energy that is associated with the internal energy or the enthalpy, and uh, it will be a critical. So it will be a critical for these reactions. So the internal energy and enthalpy, uh, it's play a major role in design and and all chemical process. So whenever, for example, if the reaction is endotherm, then they need some sort of energy to keep the reactor as in their constant temperature. Okay. If not, then the temperature might dropping too much. Okay, and if when the energy is dropping too much, maybe it will cause causing some trouble for the and maybe if you run an industry, you will have some sort of loss, right? Not a profit, but loss. And if the reaction is exotherm, then we need to calculate how much heat that we need to be transferred from the reactor, okay, so that the temperature is not increasing. Or if it is increasing, maybe we need to have some sort of safety temperature, like safety factor for the temperature, right? Okay. And for the chapter 9, because we already mentioned that one of the terms that we are going to observe is the heat of reaction. So heat of reactions, the net energy that must be released or transferred from the reactor, that is one way to evaluate. Okay. So if we use the reactions between, let's just write the calcium carbide as in your textbook for reference. So you have a calcium carbide. So calcium carbide, and then water is reactive, becomes calcium hydroxide. I think it's already in the stoichiometric, right? Hydrogen 2, 2, 4, Ca1, carbon 2, yeah. Oxygen 2, yeah, right. So if we look on the stoichiometric reactions, we need one mole, right? 1 mole of calcium carbide and 2 mole of water. Okay. So which means in our case here, we need to have this ratio to make out this product of calcium hydroxide and the C2H2, right? So what is the heat of reactions? Okay. So of course we need some energy to make this happen and to make this stoichiometric happens, because there is a breaking down, how to break down. So there is breaking down the molecules, right? Breaking down into the molecular level, so breaking down the bonds. and forming a new bond, right? Forming a new bond. So of course there will be some heat of reactions, or there will be some sort of net energy that is released during this process. And let me just look on if I make this. Okay, so for example, okay, the heat of reactions for the calcium carbide is this, okay, and we look on the definitions. The heat of reaction or enthalpy of reaction is the enthalpy change for process in which stoichiometric quantities of reactant at temperature and pressure react completely in a single reaction to form products at the same temperature and pressure. So the basis on how do we observe this heat of reaction is basically on the stoichiometric reactions. Okay, so we could say that this heat of reactions is actually the enthalpy of products minus the enthalpy of reactants. That is okay. So if you look on the balance that we need to make, that the heat is equal to the enthalpy change, then the negative signs means that 125.4 kilojoule per mole, or kilojoule as it's in the heat, it must be transferred from the reactor. Okay, so negative signifies that it must be taken away. Okay, and also if we look on the units for the heat of reactions, usually it will have a kilojoule per mole. So we need to define what mole is it. Okay, let's say we have a 2A plus B giving out to 3C, and let's say we have the delta HR for 100 degrees Celsius, 1 atmosphere, this giving negative 50 kilojoule per mole, which means that this negative 50 is consuming these 2 moles. So negative 50 kilojoule, this consume 2 mole A, and also consuming 1 mole B, and also consuming 3 mole C. That's how it works. Okay? So if you see the heat of reactions is usually per mole. What mole is it? It will be means that they will use this enthalpy or the heat of reactions to consume each of the molecules. Okay, so each of the moles in the stoichiometric proportions. Okay. If regarding to this, if 150 mole of C, okay, generated per second at the 100 degrees Celsius and 1 atmosphere, and we could write the flow. This is 3 mole, and multiply with the mole per second, mole C per second, and then this will be kilojoule per second. Okay, and in more general, we could have we call the I think we already have in the chapter when you learn chapter 4 the extent of reaction. Let me write in the new page. Okay, let me take. I think this is later. Okay, let me just write. Okay, so if we have the stoichiometric coefficient of reactant or reaction product A positive if A is product and negative if A is reactant. And we have the mole. This is moles of A that is consumed or generated at some T constant and P constant. Then the enthalpy change can be correlates with the heat of reactions at some temperature and pressure, and then divide by this stoichiometric coefficient, multiply with the mole, okay, the moles of A that is consumed or generated. And we define the extent of reactions. So the extent of reactions this subtraction between the moles that is in the outlet and the inlet for the reactions divided by the stoichiometric coefficient, or we could just write and we could then combine these two as delta H, extent of reaction, and delta H, oh it's R, sorry, delta HR at temperature and pressure. So the extent of reactions is we could define this also in how far a reaction has proceeded. Okay. Now some notes. Okay, now some notes regarding the what we have. At least some short summary for the heat of reactions and how we could calculate some of the process. First is if the heat of reactions So if the heat of reactions at temperature and pressure, if this is negative, then the reaction is exothermic. At temperature T and pressure P. Okay. And if heat of reaction is positive, then reaction is endothermic at temperature and pressure. Yeah, okay, and the definitions in terms of the bondings we already discussed before, right? Okay, second, at low pressure or some moderate pressure, the delta HR is nearly independent of pressure. So it's one of the assumptions that we are going to probably to make in some of study case. And three, the value, and this is I think important for this chapter 9, the value of the heat reaction depends on stoichiometric. So for example, if you look on these two cases, these two reactions, it's the same substance, okay? But the difference is the second line you multiply by 2, and the significance is the heat of reaction becomes twice, right? So it's really depends on the stoichiometric reaction. So if you multiply the coefficients, then the heat of reactions will be also multiplied. Okay, as I think this is because of what we have here when we are having this consumptions of the molecules. Okay, so if you have like twice of that coefficients, then you need to have twice of the heat of reactions that needed. Okay. And I think it's already can be observed directly from the value, right? The value of the heat of reaction. Number 4, the value also depends on the state of aggregations. Which means gas, liquid, or solid. Okay, it's also having a differences, okay, in the value. For example, if you look on this part, still the same substance, but you see that the state is different. The second line is having all gases. The first line is having one liquid here, right? This all gas. And has different heat of reaction. And of course, heat of reactions for liquid is having more higher in numbers because it's liquid, right? Because you need to have more energy to transform the liquid. And now, as in the last notes, that we will have what we call the standard heat of reactions. Delta HR with some sort of circle in. Also, I think specifically. So the standard heat of reactions is heat of reactions when both reactants and products are at a specified reference temperature and pressure, and usually room temperature and 1 atmosphere. So and then it becomes our standard, the standard. Okay, this 5 notes is basically the first part in the heat of reactions definitions and how we are going to use in a simple reaction, including the extent of reactions. The extent of reactions. The second part will be measuring using the Hess law. Okay. Okay, I think we can move to next session. Now the next one is, let me check if I have. Oh yeah, one of the calculations. Okay, now if you look on example in your textbook, you will see this some sort of calculation of heat of reactions. So first of all, we have this. First is the moles of for number 1. Okay, we start from number 1. So we have 2,400 mole per second of the carbon dioxide is produced. So it's produced. The stoichiometric is have 4. You can directly get the extent of reaction. That is 2,400 divided 4, 600 mole per second, and we are going to use this into our the enthalpy. So the delta enthalpy is equal, and the standard heat of reactions, and you just multiply this 600 with the negative 2,000, and you get the result. I think it's directly can be observed. Number 2, what is standard heat of reactions? Blah blah blah. Calculate the enthalpy if it's produced. These reactions are all at the 25 degrees. So first of all, if you look on the reactions, we have the carbon dioxide, right? So it has 8. So first is again same thing. Extent of reaction is 2,400 divided by 8. This will be 300 mole per second for extent of reactions. And the same way we are going to calculate. Okay. And since this line here, this stoichiometric line is twice from this one, so this should be multiplied by twice. So that's delta HR for this one is 5,000 something, right? That's not 6, 756. And then you get the answer for the enthalpy. Okay. And then the last one, we have two reactions. Heat of vaporization of butane, blah blah blah. We know the heat vaporization. Okay. What is the standard heat of reaction of this? Okay, this line. Calculate if the carbon dioxide of produced. Okay. Now first, since if you remember, if we want to construct the heat of reaction, we can construct this as H products minus H reactants. So products is carbon dioxide and water. So we could write this will be delta H R the liquid plus 5 delta HV vaporization of water, and then plus delta H vaporizations of TC4 stand. And we know that the delta H is delta H of, let me write this as R1 for this standard. Okay. So this will be negative 2878 plus 544 plus 19.2. And we got this is 2639 kilojoule per mole. Okay, and then the delta H, this will be taking the same, and I think we get, if we see it's 2400, it's 4, so it's 6, so 600 multiplied with 2639, and you get the results. Okay. Okay. And then another additional notes is if we have the internal energy of reaction. It follows that it's actually similar to what we have in enthalpy. So we have the delta UR. This is also U products minus the U reactants. This is internal energy of reactions. And we could take this into a more is this? Oh no, this is delta H. Let me write that delta UR at T is delta HR T, and using the gas constant RT gas products minus gas reactants. Which means if we have C 6H14 plus oxygen, this is liquid gas. So delta UR is delta HR minus RT. The product is 6 plus 7 minus 19 over 2. Okay. So it depends on the standard heats of reaction and the R and the temperature. Okay. Perhaps any questions? Okay, let me continue for the second part. Chapter 9. This will be the Haas law. Okay? Because we are dealing with the heats of reactions. Of course, the heats of reactions depends on stoichiometric. And by doing so, we are going to construct a stoichiometric path, right? Stoichiometric path that how we are going to form a substance, or how we are going to break down a substance through some stoichiometric reaction, and how it will be affecting the heats that we or the energy that we need, right? Okay, the Haas law, I think you're already familiar in the chemistry, right? The Haas law. And usually, when we are, I think it's learning chemistry in some laboratory on how we are going to measure the heat of reaction, we are going to use the calorimeter, right? Basically, calorimeter is a reactor that we are really having in a closed system, and yeah, it has some insulations, and you will measure the temperature, and then lastly, after you measure the temperature, you can measure the heat of reactions uh, from the energy and the reactant and product heat capacity. Okay. But of course, it's really difficult uh, to objectify the process because there are a lot of error, right? A lot of error, a lot of limitations for the calorimeter. Okay, but let me just give you an illustrations. Okay, for example, if you have a carbon, solid carbon, and you react it through oxygen, you may get the carbon monoxide. Okay. Okay, if we are going to use this in our calorimeter, can we get this carbon monoxide? But if we put, like for example, 1 mole carbon, half oxygen, I think we will never get the carbon monoxide as the final product. And the reactions, if we put this in a room temperature or lower than room temperature, probably there will be nothing that can be truly observed from our naked eyes, right? If we heat, okay, if we heated this, let me write here first. It seems impossible. If the temperature is 25 degrees, also nothing will occur. If mixture heated to a temperature where C and oxygen react, the product will be carbon dioxide, or some carbon monoxide and carbon dioxide. So when we want to, when our objective is how to measure the heat of reaction, so heat of reactions of carbon monoxide formation, this is actually what we are going to achieve. So how do we achieve this heat of reactions to find out this carbon monoxide? Okay, but we know from the descriptions, if we heat this carbon and oxygen, we will at least having a pure carbon dioxide, or we will have a carbon monoxide with carbon dioxide. So we will have at least two possibility construction of our stoichiometric path. Okay, we will have, first is construction of carbon and oxygen alone. It will be giving us the carbon dioxide. Okay, and we can measure the heat of reaction for this one. Let me take this as R1. So this will be equal to this kilojoule per mole. And second is the carbon monoxide plus the oxygen, in which it gives us the carbon dioxide. And we also can measure this heat of reactions as so. When we construct our objective that we want to that we are going to calculate this carbon monoxide heat of reactions, we may denote this as R3. So we can construct our path based on these three reactions. So reaction 3 is our goal. This is our goal. So we are going to construct first is the first reaction. Okay, we are having this carbon dioxide product. And we know that this this final product, if we take this as a reverse of reactions from this second reactions, we will get the carbon dioxide. So this delta H is actually the negative of our second heat of reactions. Okay, this one. Okay. So then we could take this, the total, okay, of the reactions, or this the R3. This will be delta HR1 plus minus delta HR2. In our case, this will be negative 393.51 plus 282.99, and this will be negative 110.52 kilojoule per mole. And if we look on how we are going to treat this based on the reaction itself, we'll look on what we have. Okay, so the first reaction here, it's the final one is here. So the first reactions minus the this reactions minus this will be giving out this carbon dioxide. Or if we take in more clear, this will be C plus O2 minus CO. This is from the second reaction, minus half oxygen will be CO2 minus CO2. This will be cancelled, and this will be going to have C plus half of oxygen, and we move out this carbon monoxide, and this will be our reaction tree if we want to make it to our stoichiometric reaction. And this is well, we have the Hasse law. I think the Hasse law is better to be explained in this way rather than looking at the definitions. Because by definition, it's actually taking the stoichiometric equations for some reactions. It can be obtained from some algebraic operations. You can multiply the delta HR, right? And then it will result in some multiplication in your stoichiometric reactions. Depends on your case. What is your goal? What is the substance that you want to find? Okay. Okay. Now, okay, let me just wait for a while. Okay. Okay, let me go through. And perhaps just taking notes for Hasse law. So the Hasse law is, if you have a stoichiometric equations for some reactions and you want to multiply or you want to construct something out of it, you can do by some algebraic operations. You can multiply, you can add, subtract, okay, on the other equation as well. And your delta H, your heat of reactions, can be obtained by performing the same algebraic operations, right, as we did in the previous example. So you can actually multiply with some constant. You can, you can multiply, and then you can force out some reactions to make it happen. But of course, you need to look out some requirements, okay, what you need and what is the limitations also, okay, because I think not all reaction can be simplified in the Hash law. Of course, the reaction should be a reactive process, which means it should have, at least in the stoichiometric, it would have an oxygen, right? Okay, I think Hash law intuitively can be understood. Okay, the next thing, okay, aside from what we have in the reactive process, so aside from the heat of reaction in general, the second one is the Hess law. The third one is the heat of formations. Okay, heat of formation. It's a standard heat for forming a compound. Okay, so we will have the, the title is formation reactions or heats of formation. Let me check if there's any other. Okay. The formation reaction is the reaction in which the compound is formed from its elemental structures or constituent or structures, I think, as in nature. Okay. For example, of course, if you have oxygen, it will have with two atoms rather than one, right? And the enthalpy change associated with this with 1 mole of the compound at a reference temperature and pressure, usually 25 and 1 atmosphere usually, is called the standard heat of formation. Standard heat of formation. We could write these symbols with HF like that. And you can see some of the example in table B1. So table B1, okay. So by now you could have listed, okay, some of the functions for your appendix, okay. So table B1, B2, B5, 6, 7, 8, 11. That is, I believe, important for at least for final exam. It will be important for the energy balance. So, for example, if you have ammonium nitrate, you will have nitrogen. C is for crystal. Delta H R is negative 365 kilojoule per mole. And if we check table B1, is standard heat formation is the same, which means that this heat of reaction is the standard heat of formation. Okay, the same. And we could construct the correlation between this heat of formation with the heat of reaction, which is the same thing. At some cases, that is we could construct through some coefficient for stoichiometric for products and reactants. Okay, so you could just multiply with each enthalpy of the standard heat of formations from the product minus standard of heat of formation from the reactant. So of course, if we have like multiple stoichiometric reactions, we need to emphasize which one that we are going to achieve, okay, and then we construct the which compounds that we are going to break down, and that by this breakdown means that you need to construct this balanced equations for finding the heats of reaction of the reaction that we want. Okay, this is heats of formation. Okay. Now another list that we have is the heats of combustion. So heats of formations. Okay. In a short summary, heats of formation is the heats or the heat of reactions when you form the compounds. Okay, and it's constructed by its elemental structure or its elemental constituent. And you can see the from some compounds in the table B1. Okay, so next is the heats of combustion. Okay. We can write as the standard is with C. So this is standard heat of combustion. So this is heat of combustion that of that substance, okay, with oxygen to give results or to yield specified products. Specified products. The product is carbon dioxide and water. with both reactants and products at 25 degrees Celsius and 1 atmosphere. And also you can check this at table B1. You have some list of standards listing some standard for this heat of combustion. So if you check the ethanol in the table, the ethanol has the combustion negative 1366.9 kilojoule per mole. This means that the ethanol, when it reacts with the oxygen, and we can see that this is what it means. It's at 25 degrees Celsius, 1 atmosphere. This is 1366.9 kilojoule per mole. That is the definition on the heat of combustion. And you can also take some similar approach with the heat of formations that you can have the for heat of combustion as well. So of course the heat of combustion will be only involving the combustible substance or combustible products that can be calculated from the standard heat of combustion standard. And all the heat of formations, heat of combustions, how we are going to deal with in some case study. Of course, we are going to need the tools. The tools that we need is the Hash law. So by requiring the Hash law as our some sort of guidelines to make sure that we construct a correct stoichiometric equations that we want, and we are going to have some sort of algebraic operations to make out our heat of reactions, which one that we are going to achieve. And after we are having that heat of reactions, then we are going to check whether it's correct or no, and then check with the equation, the stoichiometric equation. I believe it's very similar with your, I think in your basic chemistry, right? But now it's more detailed. You have defined this in some standard terms. Like for example, some compounds they have some standards for their heats of formations, heats of combustion if they are combustible products. So you can make out those in several way also. Okay, so that's all the uh, the terms in chapter 9 for a reactive process. So start with the heat of reactions, okay, and then we have the hash law for guiding the construct the path, right? To construct the stoichiometric path, and then the standard of heat formations, heat of combustions, and then now we are going to see in more general how to proceed our energy balance process. Okay, this is the summary. Okay, so the general procedures. So for energy balance, on reactive process. Okay, general procedures. So first is, of course, as we did in the previous chapters, in the chapter 7 and 8, okay, and I think from the chapter 4 also, that the first thing we can do is we draw and label flowchart or diagram, right? Which one's the input, which one's the output, labeling and naming all the terms, the constants, the numbers, okay, and then use material balance or mass balance, and the phase equilibrium relationship to determine how many stream components, okay, that is possible. The reference state, choose the reference state. Choose reference state. This is for specific enthalpy usually. Or the specific internal energy. And then fill in the table, right? I think it's usual, the same as the chapter 8, right? And then the next one is calculate the flow. Okay, it depends on the situations. And then complete the calculation. Complete the required calculation, whether it's finding the heat, the total heat, or anything that you miss out at the very beginning. So now, what's the deal with our? This is actually general procedure for all process like that we have, right? So what's the deal with the chapter 9? Okay, with the chapter 9, we are dealing with the heats, right? The heat. So we are going to have two approach. Okay, two approach. First is heat of reaction, and the second is heat of formation. So first is, let me give you a context to help out our the illustrations. So perhaps we are going to use some process. Okay, so the example is using the propane. So for example, we have this structure. We have this flow chart. We have 100 mole of propane that is going inside at room temperature, and then we have the 600 mole oxygen and 2256 mole nitrogen that is going to inside also in the temperature of 300 degrees of Celsius into a furnace, and the result of the product will be oxygen, nitrogen, carbon dioxide, and water vapor, right? And they have all they have all moles, right? And it's given that the reactions we have propane plus the oxygen, it's giving out the carbon dioxide and water, right? And you have the delta HR is negative 2,220 kilojoule per mole. The first method is called the heats of reactions. So this picture is actually what we have at the first and second. So we have already dealt with this. So the heat of reaction method. Usually, this is we are using it if only single reaction. For delta HR known. Okay. So first, of course, complete material balance. Second, choose reference state. Let me just make some suggestions. The best choice is reactant and product at 25 degrees Celsius, 1 atmosphere. This will be the best choice because this is the standard usually using, the standard is using this 25 and 1 atmosphere, right? So we can take this as our reference state. And also for some gases at this 25, 1 atmosphere, we can check the table B8, right? For the enthalpy. And then calculate the extent of reactions. For example, in our illustrations, we are using the for the propane, right? So this will be equal to because there is no propane outside, they are all converted into the gases. So we will have 0 mole at the outside, right? And minus the inside is 100. And the stoichiometric is just 1 for the coefficient. So we have 100 mole per second for the extent of reaction. And you can also check for other species as well to check whether we are having the extent of reactions. Okay. And then we can compare the results. And you can verify that this extent of reactions is independent of the species chosen. Okay. And then the later part is prepare the reference table. I think we can go to the next slide because I think it's too close. Or maybe let me go. Well, I don't think we can have here. I think we can just write another one here. So enthalpy table as usual. Enthalpy table, I think I have here. So we choose the reference at the 25 and 1 atmosphere, 25 Celsius and 1 atmosphere. And then we insert all the inlet and outlet enthalpy table. All the moles we are inserting, the propane, oxygen, nitrogen, and moles that is out in the outlet, we input all. Okay, and since if we look on the diagram, uh, the the standard temperature, the 25 degrees Celsius, is on this propane. So we could take the propane enthalpy as 0. And we could look on the other enthalpy as well for each one of them, for oxygen, nitrogen, carbon dioxide, and water vapor. Okay. So next, of course, we are going to calculate the enthalpy, right? Enthalpy component. For example, the H2 can be obtained from the delta H on table B8. So delta H for oxygen, 25 degrees Celsius, is going to be 300 degrees Celsius, and the delta will be 8.47 kilojoule per mole. Because we say that this is our reference, right? This reference, the 25 is our reference. And we are doing the same thing with the H3, right? And H4, H5. We're doing the table B8. H6 also, and H7. Okay. But I think the H7 we could also check using the steam tables. Okay. We could use the H7 as we could take this into our integrations for the CP from 25 to 100 CP for liquid, and plus the heat of vaporization when you are going to phase change from this at the boiling temperature 100 degrees Celsius, and then plus you're going to increase until the 1000 degree of Celsius for the CP at the vapor, some vapor here for the vapor for the water vapor. And then after we get all the enthalpy, of course, it depends, right? You use the H7 in the table B8 or using this integration here, it's actually depends on your assumption. And then calculate the delta H. So we are using this extent of reactions. Wait. This is for single reaction. If you have multiple reactions, then you have the extent of reaction for some of the equations. So let me just reach the sum for extent and the standard heat of reaction. Plus and minus this is for multiple reactions. And substitute all with the our moles and enthalpy. We could get the delta H, and then lastly the energy balance. Actually, we are still using the same within the chapter 7. If you still remember, this is the heat minus the work. This is the delta H plus delta E plus kinetics plus potentials. This is open system, right? And calculate the required calculation. As usually the work is 0, kinetic 0, potential 0, usually, because the enthalpy is much larger and significant rather than this kinetics and potentials. Okay, so that is heats of reaction method. So what's the deal with this method? Okay, so first, what you are going to have is in the single reactions, why this is readily you can directly use this method if, okay, you have a single reactions and you have this heats of reactions known. Okay, so you have this already. Okay, this equation already have. Okay, you have this. Okay, but what if this information is not given, and maybe you are just giving out the conditions but without any context on the stoichiometric and also the heats of reaction? Then we can go to the second method, which is the heat of formation. Basic is the same. The difference is how you get the heats of reactions. Okay, that's the difference. The heats of formations, you are going to construct your stoichiometric equations from the heats of formations that are available either in the table, okay, for some substance, and either from any other sources. Okay. Okay, so the second one is the heat of formation. So let me write this as heat of formation. So this is easy for multiple reactions. Or single reaction. With the delta HR is unknown. Okay, so of course the first part is complete material balance as usual. That's, I think you need to be aware of that. And then just reference state. And usually reference state should be just taking the 25 degrees Celsius and 1 atmosphere, and that's going to be simplified all. And also you can check the table B8 for some sort of a specific enthalpy for some gases, right? For if it is gas, and then the enthalpy table. Now we are going to actually it's similar, but the difference is we are going to have the enthalpy at the propane. So this is not 0, this is the H1. Okay. And then calculate So this is not the C3H8. This should be the the carbon. That is the reference state. So all the elements will be the reference state. The gas elements without the, so all the elements, so this will be hydrogen gases, and then the without the carbon dioxide. And then calculate the specific enthalpy. And now we are going to check the delta H from the delta H F. This is based on table B1. And then we can also use table B2 and also B8 and B9, and also the latent heats at the table B1. This is for CP, this is for enthalpy for gases. This is for latent heats. Now the H1, for example, we could write down first the reactions. This is all in 25 degrees Celsius, 1 atmosphere. And we could write this as H1 as the standard heat of formations for the propane, for the gas propane. And based on the table B1, this is 103.8 kilojoule per mole. So how do we read this process? So the H1 is enthalpy of propane at 25 degrees Celsius relative to C and H2 as a reference state. Okay. So basically the deal with this is why we are going to use the heats of formation, because we are not getting the information of our heats of reactions. Okay. And using the table B8 for all the gases. So table B8 we'll be using for the H2. I think it's similar with previous one, H3, H4, H5, until H6. And also I think H7 we can also consider to use the same. And for 6 and 7 we can also consider to check some heating terms, right? Because it's going to be heated from 25 degree to 1000. So perhaps using the CP for table B2, right? And then lastly, the number 5 from the from this method is similar. We calculate the delta H. So delta H can be calculated from Okay, now heat of reactions terms is not required, right? Because we choose the elements. Okay, let me write note. Because elements are chosen as reference states, then heat of reaction terms are not required. This means that if we choose this carbon, oxygen, nitrogen, and hydrogen, they are all our reference state. We choose that as our reference state because we are not sure on our heats of reaction for the standard one. It's not given. Okay. And then substituted the delta H into energy balance and complete the required calculations. And to see more observations is basically the difference. The difference for heats of reactions, what you need is you need to have, I think because it's already been given, the heats of reaction so you need just to consider the reactants and products at 25 degrees Celsius. This is your reference, okay? This is your reference state. For heats of formations, because you are not given any heats of reaction, so you don't know what kind of reaction it will be and how much you need to heat. So you need to consider the formation from the elements. So you can choose the reference state from the elements at the 25 degrees Celsius. And then we could see how the constructions, the construction it will be. And for some multiple reactions, you need to list the stoichiometric, and then also maybe using some Hash law to make some required calculations for some stoichiometric equations. Okay. Later on, we will see some examples. Okay. And yeah, we will see some examples, especially example on your in your textbook. And the last thing on the chapter 9 for the calculation is the thermochemistry, for thermochemistry of solutions. And yeah, I think that will be the last. Okay. Really, the last part of this discussion is adiabatic flame temperature and some other terminology that you can read from the textbook. But we will not really discuss about that. And I think we will finish this on next Monday. And as usual, I think I will just give you additional videos for some selected for some selected problems. So you just wait for my additional video. Meanwhile, I have uploaded chapter 8 videos for some examples. I just did 2 examples, but I would think I will make another one. Okay. And we will include the chapter 9 also. Okay. So chapter 9 is actually not that much. Okay. I think chapter 8 is having really a lot of content considered with the chapter 9, right? Okay, I think that will be the end of our lecture today. Okay. I will review this next Monday, if you, or maybe just giving you one or two example on this delta HF or delta HR, okay? How to compute into the energy balance. Okay. And Yeah, as I mentioned in the early class, okay, since we have 9 participants today, um, let me stop the sharing and let me do the uh, okay. I think we can have some pollings one more time. Okay, please. Okay. So 8 students. Supposedly we have good um, good schedule. For example, a few want to have on Monday. I think that's still okay. 6th of June. Okay, 2 students not answering. All right. So we have 4 students choosing the Thursday, 2 students choosing Monday, 2 students didn't answer. So I think Thursday. Okay, Thursday. Okay, do you agree? Thursday, 9th of June will be our final exam. Uh, Chantong feels sad. Anna he also feels sad. We have
Can
another finals, right?
no, I mean, if we have the score on ninth, then probably when will we receive the last results for this subject?
You mean the when you will have the results? Yeah, I
Yes.
think if we have in the afternoon finish, I think in the night you will have the results.
Okay.
Yeah,
Thank you.
yeah, okay. I think do we have any other opinions about the final? If not, then I will just make 9th of June will be our final exam. We will be using the WebEx. We'll use several, maybe 2 platforms to make our finals. The first platform is like a game. The second platform is like the last time you did the quiz. Using these two platforms. Okay, I think that's all for today. So you can uh, you can leave the meetings if you want. So that's all for today's class. Okay, and thank you for joining. Okay, thank you. Yeah, really, you're welcome. Yeah, you're welcome, Ricardo. You're welcome, Georgie.